heresies today, at least something that is considered to be a heresy. Please feel free to operate. Yeah. This was a joint work in collaboration with some of our colleagues, Kacper Dębski, my PhD student, Szymon Harzyński, who is here somewhere, and the dean of our, pro-dean of our department, and Artur Reichert as well. And this is a continuation of our earlier work on weird proposal to extend special relativity in order to explain quantum phenomena. And I would like to start with a simple problem that you can give to students to solve. The task is to find all linear transformations that preserve the speed of light. Something that is being shown, in fact, in the first year lecture course on Introduction to Classical Mechanics, right now being taught that derivation leads to Lorentz transformations. However, this is not the only solution. This is a solution that's being presented to students, not to cause any disruptions, but there is also an extra possibility, an extra family of solutions that involves frames that involve velocities that are larger than c. So this is the familiar Lorentz transformation branch of Lorentz transformations that involve velocities smaller than light. This is another family of transformations that involve velocities larger than light. All of them satisfy all the requirements. All of them are linear, obviously, and they preserve the speed of light, which can be seen by looking at the expression for the space-time interval between two events. That other family of solutions transforms this space-time interval into this. So it changes the sign of the interval. However, the zero intervals are preserved. Zero interval here is equal to zero interval here, which means that if something moves with the speed of light in the subluminal frame of reference, it is going to move with the speed of light in the superluminal frame of reference as well. So mathematically and technically speaking, both of these solutions are a complete answer to the student's problem that should be given. And then we can decide if we like that other solution or not. We can cross it out by saying it's unphysical or not, depending on our mood. The question, however, is whether this simplified scheme that works in 1+1 dimensional case also applies to fully 1+3 dimensional case that is relevant to us. And this is the purpose of this talk, and the paper that I'm going to talk about shows that one can generalize this to 1+3 dimensional case, and apparently all special relativity makes sense and works even for superluminal observers. I will discuss the conditions and circumstances, but the takeaway message that this is possible, and this does not lead to any obvious paradoxes.
So to be strict, we should also add that it's 1+1 dimension.
Yes.
Yes,
I just said that. So this is the work that we've done before with Artur, where we show that the obvious problems with superluminal phenomena involving alleged grandfather paradox and others, in fact, are not serious enough to be that concerned about. And we have shown that in fact, superluminal observers and phenomena lead to some sort of disturbance of causality as expected. However, these are not serious hardcore paradoxes, but rather we claim that this, in fact, is indistinguishable from what we know, what we call quantum theory. So the idea is that, in fact, quantum theory is a consequence of special relativity extended to superluminal observers. And these violations of causality, so-called, that appear in special relativity are nothing more but just quantum mechanical indeterminism that is known and studied for 100 years. In fact, this year's Nobel Prize is awarded to experimental validation of these properties. But I'm going to talk about 1+3 dimensional case. And I would like to begin with just very quick crash course on how to generalize Lorentz transformations to 1+3 dimensional spacetime, something very trivial. So first of all, Lorentz transformations do not change the perpendicular component of spacetime coordinates. So if I'm moving along velocity v, then the perpendicular components, which are given by the vector r minus the parallel component, does not change. It's preserved by Lorentz transformations. the longitudinal component is just Lorentz transformation. So the longitudinal component of the spatial coordinate changes according to the Lorentz transformation. And if you add these formulas up and also complement them with the transformation for the temporal coordinate, you get a three-dimensional Lorentz transformation formulas. This is Lorentz transformations independent on the choice of the direction of velocity. So if the observer moves along any direction, v, this is the Lorentz transformation you need to apply. And that concerns two inertial frames of reference in relative motion along velocity v that are unrotated. Okay, so the question is, what happens in the superluminal case? These transformations obviously preserve the space-time interval as expected. The question is how to generalize the same thing to 1 plus three-dimensional case for superluminal observers. So let me first analyze what happens to the space-time interval according to what we have said so far. So suppose that we are moving along the direction x for simplicity first. So we already know that this part of the interval changes the sign. So t prime gets a minus sign, x gets a plus sign. And if you add two extra spatial dimensions, let's call them psi prime and chi prime, they do not change, which means that they have the same sign as before. So this is what happens to the space-time interval. And clearly there is something fishy going on because the structure of space-time interval is not preserved, it changes, which is an indication that the superluminal frame of reference will not be indistinguishable from the subluminal frame of reference. There will be differences, there will be physical differences between subluminal observers and superluminal inertial observers. I'm going to discuss this later. So what we are going to do next is we are going to adapt the orthodox definition of how time and space are defined in special relativity and general relativity. Namely, we will say that if something has a negative sign or if something has a given sign in the metric, like in this case, we'll call this temporal coordinate, and all the other components that have the opposite sign will have the spatial will be spatial dimensions. And similarly, we already know that this dimension here is a temporal dimension. We know that because it coincides with the trajectory of the superluminal observer. This is a spatial dimension, and we have an extra pair of dimensions that share the same sign with this temporal dimension. So we will adapt a convention or assumption. This is like the whole assumption of this scheme, that in fact these three dimensions form a three-dimensional structure that is temporal. So we will assume that in the superluminal frame of reference, there are three temporal dimensions and one spatial dimension. And we will take that hypothesis and we will investigate the consequences of that. By the way, in the literature, people have analyzed this having different approaches. Some people said that, in fact, the space in superluminal frame of reference is non-Euclidean, and that discriminates those frames from subluminal frames. We will adopt the different interpretation. We just assume that whatever has a minus sign, it must be time. Whatever has a plus sign must be space. And you'll see where do we go with this. So for that reason, we introduce a vector t, bold-faced vector t, and this is our space-time interval defined in the superluminal frame of reference. One thing to notice right away, that there are two interesting observations one can make here right away. So first of all, the metric is different in superluminal frame of reference. That's why these observers will be distinguishable from the subluminal observers. So principle of relativity does not apply anymore. It is possible to discriminate physically superluminal and subluminal observers. However, as you can see here, and I will discuss that in detail for an arbitrary velocity, because this relation holds for any velocity, not only the velocity along the direction x. Since this space-time interval does not depend on the choice of the superluminal velocity, it's the same for every superluminal velocity. That means that all superluminal observers are indistinguishable among each other. So what you can read from this formula is that there are two families of observers, subluminal and superluminal, these families are distinguishable, but within each family, there is no physical differences between the observers. So you can call them inertial. Yes.
But I don't understand what that really physically means, because it refers to the sign, which is your choice. I mean, you can choose one sign or another sign. It doesn't change physics. So what is the physical meaning of distinguishable and undistinguishable? Which sense they are indistinguishable?
I'm going to argue a bit more about this maybe later on. What I mean by this is the metric is different in these frames and in these frames. The metric tensor is different. This one has 1 plus and 3 minuses. And well, in fact, here, if we adopted a convention where the time has always a plus and the space always has a minus, you would have to write that if this is a metric times like 2, let me write it maybe. I don't know if it's going to be visible in Zoom, but this is the formula I removed from this because I didn't want to cause any problems, but maybe I should write. So if I write a metric tensor for any space-time, for any 4 vector, then we can adopt a convention where this is minus eta mu nu in the superluminal frame of reference, x mu prime, x nu prime. And these tensors are different. So this has 1 plus 3 minuses, this has 3 pluses and 1 minus. And what it means, what do we understand by this, I will try to explain later on. But in particular, if you write down Maxwell's equations in a superluminal frame of reference, they are different. They have a different form. And not just signs, there are more differences. Okay, so if you follow the same logic that we did in the case of Lorentz transformations, this is the three-dimensional, one plus three-dimensional depiction of Lorentz of the superluminal branch of solutions. As you can see, what we have on the left-hand side is the prime coordinates corresponding to the moving observer. There is a single spatial dimension r prime and 3 temporal dimensions t prime. And these are the formulas. And we can study what are the consequences of these formulas. One related comment to what you have said is that sometimes I hear an opinion that in fact what we call time, what we call space is a matter of convention. And as you said, you can flip signs and doesn't change any physics. Well, in fact, there is one physical principle that you have to stick to that says that if you have a moving observer, then what you call time for that observer is component of spatial dimension that is along the trajectory. Or you could also say that space is something that is perpendicular to the trajectory. So there is a physical difference between space and time, although from the mathematical point of view, they only differ by sign, but there is a physical difference. And you can define what space is by saying that this is subspace of space-time that is perpendicular to the trajectory. And in this case, you know what you have to call time, you know what you have to call space, even in the superluminal case, if you want to stick to that principle. So let me look at some properties of these formulas. You can consider a limit of v going to infinity, so an infinitely fast-moving observer, and that takes these formulas and turns them into this. So this is an interesting limit of these formulas. Notice that the limit does not depend on the direction of velocity. Wherever you move with infinite velocity, that results in this transformation. And what else? A major problem here is to understand what it really means physically to have time that is three-dimensional. You have to attach some physics to it. And in particular, it's even hard to define what basic kinematical concepts are in a scenario where you have more than one temporal dimension. So we were looking at the question, what do you call a velocity in a superluminal frame of reference? Because normally velocity is defined as the derivative of a position that is vector over time. Now the situation is different because in that frame of reference, you have a single spatial dimension and 3 temporal dimensions. How do you even define a velocity? So in order to answer this question, we have considered the following reasoning. First of all, you have these transformations, and you can also find the inverse transformation. And for the orthodox subluminal case, the task is very easy, because instead of inverting linearity equations, you can simply plug in v into minus v, and that's it. So you exchange primes with non-primes, replace v with minus v, and that's the inverse transformation for the regular Lorentz transformation case. Here we cannot do it a priori, but we can invert linearity equations. And it turns out that if you do that, if you invert the equations, the inverse transformation does correspond to replacing v with minus v. So this is still fine, which means that you can expect that if the superluminal observers move with velocity v relative to the resting observer, then the resting observer should be moving with velocity minus v relative to the superluminal observer. But how do you even define v? What is v if you have more than one time, right? So that's the question we're asking. And yeah.
And now I don't understand, what does it mean, the resting observer?
Unprimed observer, right? Let me. So there are two observers. One is subluminal, one is superluminal. I'm going to call.
The notion of being superluminal or subluminal depends on the observer with respect to which. Yes.
Okay, so there are two things. I
don't see how it is compatible with what you said, that they are physically distinguishable.
Yes, I will be happy to answer this question in one slide, okay? Because then things will be more obvious.
No, my problem is really that I'm perfectly fine with this superluminal branch.
Mm-hmm.
But if you start talking about subluminal observer, you must show first that description of physics in terms of Bose is self-consistent.
Yes, that's the goal.
Start with.
That's the goal, and it's usually not consistent. There is certain conditions that must be satisfied in order for physics to be consistent. I'm going to discuss this at the later part. But in general, these descriptions are not consistent, and you will find a set of conditions that will guarantee consistency, and that's going to lead us to, well, interesting conclusions. So I'll keep in mind your question. Just give me maybe 3 minutes. So first of all, in order to define velocity, we have chosen the following reasoning. We have considered a origin of the resting or subluminal frame of reference, r equal to 0. And we just plugged in r equal to 0 to these equations. And we know that according to a superluminal observer, that point, that origin of the frame, should move with velocity minus v. And if you plug in r equal to 0 to the equations, this is the equation that you get. This is an equation linking velocity and the dependence between space and time in the superluminal frame. And you can think that this, in fact, is a hint how you should define velocity, because you know that this should correspond to a motion with velocity minus v. So if you want to define what it means to move velocity v, all you have to do is switch the sign. You can compute v squared by taking scalar product of the equation with itself, plug it back, and this is the result. And so this inspires a definition of velocity in a superluminal frame of reference, which is the following one. You have to take a derivative of position over the modulus of t prime and multiply it by the versor along t prime. This is the only reasonable definition that you can derive from there. So, and if you take that definition of velocity, you can compute the velocity transformation formula from these equations, like you normally do in special relativity. It looks slightly more complicated than normally. So this is a three-dimensional velocity transformation formula, but what we should be concerned with is a special case. I mean, not the velocity transformation for the vector velocity, but let us compute the velocity transformation formula for the magnitude of velocity. And this is a much simpler formula, that is a special case or kind of follows from the general formula above. And you can now look at this formula and maybe you can answer your question. So first of all, in this formula, there are three velocities. There is a velocity of the moving frame that is superluminal, capital V. There is a velocity of some object moving with small velocity v, and that can be either subluminal or superluminal or luminal. V can be anything. And v prime is that velocity seen from the perspective of the superluminal observer. So this is just a regular scheme where you transform velocity v to v prime by moving with velocity capital V. Now, this is always positive because v is superluminal. This is also always positive. So you see that if this bracket is positive, so must be this bracket. And if this bracket is negative, so must be this bracket. And also, if this is equal to 0, then this must be equal to 0. And this already shows that if something moves with the speed of light in subluminal frame of reference, like a regular light, then the speed of light in the superluminal frame of reference is also equal to c, because this is also 0. So one conclusion that you draw immediately here is that if you define the velocity the way you did before, one conclusion is that the speed of light is preserved by these superluminal transformations. So going back to the student's problem to solve, now in 1 + 3-dimensional case, technically speaking, if you ask a student to find all linear transformations that preserve the speed of light, Lorentz transformations is not a complete answer, because these superluminal transformations also preserve the speed of light. You have to, of course, remember how to define velocity in that frame, and that's non-trivial part to define them properly. But if you define them properly, the speed of light is still preserved in the superluminal frame of reference. So again, to rule out these superluminal solutions, you need an extra assumption that they are unphysical, you don't like them, whatever. But mathematically speaking, they are valid solutions that satisfy all the requirements. So that's an important observation. Now going back to your question. If V is subluminal, which means that this is positive, then V prime will be superluminal, which means that this is also positive. So on one hand, moving with subluminal velocity is relative, because if a velocity is subluminal for a subluminal frame of reference, it is going to be superluminal for a superluminal frame of reference, and vice versa. If I'm observing a superluminal particle that moves with a superluminal velocity, then for a superluminal observer, that particle moves with a subluminal velocity. So moving with a superluminal velocity is relative. However, what is not relative is being a superluminal or subluminal observer, because there are physical differences. There is no principle of relativity that you could apply, because subluminal and superluminal velocities have a different metric tensor.
So if I understand correctly, superluminal objects in a superluminal frame are actually subluminal.
Yes, and there exists a rest frame of a superluminal particle that you can introduce. So this is kinematics. Let us not yet talk about causality and everything. In fact, we have addressed the causality problems in the previous paper. And previous seminar I was giving about this, so I'm not going to go into these details. Right now, I'm focusing on kinematics dynamics and how they are constructed. Paradoxes like grandfather paradox and everything else I have already covered before, so I don't have the time to talk about it today. But the takeaway message from this part is that kinematics is well defined. Mathematically, it satisfies all the requirements again, preserves the speed of light, is linear. What else? Well, what is not satisfied is the principle of relativity. So unlike in the 1 + 1 dimensional case, you certainly would be able to discriminate whether you are a tachyon or not, because you have different physics. And probably that's the major problem with these superluminal observers that people had by calling them unphysical. What they really meant is that they are not going to be indistinguishable from subluminal observers. And if you just drop that expectation, then you can just continue with regular investigations. And I don't see any obvious problems. Kinematics is well defined. Okay, let's go to, unless there are some questions or comments. Yes, I will talk about them last. Yes. So I'm going to briefly show you I'm not going to go into derivation. It's quite straightforward, actually. But I'm going to show you the result. How do you have to define an energy and momentum of a superluminal particle in subluminal frame? So if I have an object that moves with a superluminal velocity v in subluminal frame, these are the expressions for energy and momentum. They look almost the same. You have to flip the sign here. There is a important difference, though. And sometimes superluminal particles are called ones that have imaginary mass. And this is not correct. Imaginary mass would mean that there is just this change, but there is no sigma here. That sigma has to be either plus or minus. And that sigma has a non-trivial transformation properties, which are not captured by saying that tachyons have imaginary mass. It's not entirely correct. So to complete these formulas, first of all, sigma has to be the plus or minus. M is some parameter that you can call a mass of a superluminal particle. You can immediately see that the smaller the velocity, the larger the energy. So you cannot slow these particles down below the speed of light. So again, it's the same for normal particles. You cannot accelerate them too much. You cannot exceed the speed of light. So in fact, you cannot cross the speed of light in any direction with any object, whether subliminal or superluminal, because there is this energy barrier. However, there is no problem whatsoever with these particles existing and being superluminal all the time. So this is the physical reason for this. You cannot slow them down because there is not enough energy for this. What is important is that this sigma has a non-trivial transformation properties. So first of all, notice that energy can be either positive or negative. And consequently, momentum can be either along the velocity or perpendicular to velocity. Parallel or anti-parallel to velocity.
Excuse me, I'm puzzled because a moment ago we told us that you have 3 times and 1 space.
Yes.
And now you have 1 energy and 3 momentum.
Because we are characterizing.
So they are associated with what?
They are associated with a subliminal observer. So there is a subliminal observer that has 1 time and 3 spaces, and he observes or she observes superluminal particle. But you are completely correct. If you transform this to a superluminal frame of reference, you will have 3 energies and 1 momentum. So everything is just you will have to change dimensionality of major physical quantities if you transform them to superluminal frame of reference, that's why I'm at this stage only characterizing energy momentum for subliminal observers. Now, it is interesting that sigma can be either plus or minus, and in order to characterize energy of a particle, it's not sufficient to say what is its mass and velocity. You have to add an extra information, what is sigma, if it's plus or minus. And this is a consequence of the fact that this 4 vector is space-like, because P is greater than E in terms of magnitude, which means that a simple Lorentz transformation can change the time-like component of the 4 vector from plus to minus. And this is captured in this formula. Sigma can change the sign for sufficiently large velocity, subliminal velocity. So if V is subliminal, you can flip the sign of sigma from plus to minus or vice versa. And that means that you cannot force energy to be always positive. You have to deal with negative energies. This is one of the consequences of these considerations. Energy does not have to be always positive. It can be negative sometimes. And you can address this by saying that the major difference between tachyons and normal particles are such that normal particles are either particles or antiparticles. And an electron is always an electron in all inertial frames of reference. Lorentz transformation does not change an electron from being an electron. For superluminal particles, this is not the case. And you can turn a particle into antiparticle by a normal orthodox Lorentz transformation. That's one consequence of this. So you should expect that if superluminal particles existed, their nature would be to change particle into antiparticle by just doing Lorentz transformation, subliminal Lorentz transformation. One of the consequences. In fact, this has been discussed in detail. This aspect of this has been discussed in detail by George Sudarshan many years ago in the 60s, I believe, and he already observed this, and he said that there is nothing wrong with that. You can always reinterpret particle into antiparticle, and there are no problems associated, standard problems that are associated with the fact that negative energies lead to some paradoxes. He argued that this is not the case, and I also agree.
I have a question because from this it follows that these two possible values of sigma should exist for all objects. So also for particles which do not have their antiparticles, right?
Yes, I mean particles can be antiparticles can be identical with particles. Yes, but
yeah, but then you cannot say that you have like two different sigmas unless you add some extra degree of freedom that is not in our physics. Right?
In a way, you're right. So in a way, if you draw a space-time diagram of a particle and draw a line, this is insufficient information to specify what is the energy. You have to add this extra bit of information whether this is a particle or antiparticle, even if they are considered to be identical.
Yes, but then we should be able to observe it, because if there are more degrees of freedom that we expect, then we should see it, for example, if they are fermions and
if they interact with our matter, yes. And I will talk about that at the last stage, because I believe that there is a chance of experimental observation of this phenomenon. So this is energy momentum. Now, what about dynamics? And this is yes.
So on your previous slide, can it happen that this signal is the bracket is zero? So the field that you have.
Yes, it is possible, and in that case, it doesn't matter whether sigma is plus or minus, because that corresponds to a particle moving infinitely fast. An infinitely fast moving particle has a zero energy anyway. Okay. And momentum, whether it's left or right, doesn't matter. It's the same thing. Let me explain why. So, for example, let me consider a diagram where a superluminal infinitely fast moving particle is emitted from another particle. Okay. It does not matter whether momentum is this way or this way, because if the momentum goes this way, that means the particle has been emitted. So these are particle 1, 2, 3. Then you would say that momentum P1 plus momentum P2 must be equal to momentum P3. If you draw an arrow in the opposite direction, that means that this is an absorption, not emission, and you in fact should put P2 on the other side of the equation. And that corresponds to the opposite sign, which means, and both equations are the same. So it does not really matter whether momentum is to the left or to the right. So that's that special case does not spoil anything. Okay, so now I would like to address the important question, whether you can have a covariant dynamics involving both families of observers. And that was the question that you raised before. The answer is, in general, no. And let me show you why. So when you talk about dynamics in any theory of physics, you often like to formulate it in terms of the principle of least action, where you have certain function, call it action, that is defined as an integral of some Lagrangian over time. And you want to minimize that. And the actual real dynamics corresponds to minimum action. Now, this Lagrangian can depend on the degrees of freedom of your system, whether it's mechanical particles or fields or anything else. There are some degrees of freedom, some configuration space that Lagrangian depends on. Now, going back to what it means to have more than one temporal dimension. If we want to take that assumption or hypothesis seriously, and that's our goal, to take it seriously, you would say that in a superluminal frame of reference, analogous expression for action should have this form. So if I'm a superluminal observer, I would like to formulate the principle of least action, and I in fact have more than one temporal dimension. I need to consider a Lagrangian that needs to be integrated over all 3 times. This is our assumption. Okay, this is how this concept generalizes to superluminal frames. These 2 pictures contradict each other in most cases. Why is that? Well, for example, if you have a single mechanical particle that is a solution to some Euler Lagrange equations, the solution to these equations is a one-dimensional trajectory, a line. If you solve this equation, the solution is not one-dimensional, it's 3-dimensional. It's a 3-dimensional manifold. So a trajectory of a system would correspond to a 3-dimensional volume dynamical object that has 3 dimensions. And that clearly is in contradiction with this. So if you consider any object, whether subliminal and superluminal, and you want to consider that object from the point of view of both these observers, they will give you different descriptions. That's not covariant description. This cannot work. So let us go back and see what can be done. How can you fix this? And if you can fix this at all, or this just fails in any case. So let us assume that we have some degree of freedom, some configuration space of states of the system that we could call psi. Whether it's position or number of positions or anything else, let's call it psi. And let us assume that we want a covariant theory that can be described both in subluminal frames of reference and superluminal frames of reference. So we want to keep this. And we will also say that if you perform a superluminal transformation, that psi will transform itself into some psi prime. And that is the description of the system, of the state of the system in the superluminal frame. Okay. We also want that doesn't matter whether you describe your theory in the subluminal frame of reference or superluminal frame of reference, the solution should be the same. They should be equivalent, which means that if you solve Euler-Lagrange equation in this frame or this frame, the outcome is going to be the same, which means that you can actually impose this by imposing that S is equal to S prime. Because in that case, trivially, what minimizes S will also minimize S prime. And that will guarantee that if psi minimizes S, then psi prime will minimize S prime. Okay. Now we can write down S again and transform the state of Lagrangian, actually the state of the system in Lagrangian, to the superluminal frame of reference. We can just transform this expression by applying the superluminal transformation, and that will take psi into psi prime, and that will take T into R prime over C. We can, for simplicity, consider a infinity fast transformation. We just exchange time and space. This is a transformation of S to the superluminal frame of reference. You can also do another thing. You can start with a superluminal frame of reference and this definition, and transform this into subluminal frame. So we can transform psi prime into psi and T prime into R. And now we want to impose that S is equal to S prime. So you should expect equality between all these integrals. In particular, there are two equalities that we'll be interested in. One of them says that L of psi should be equal to L prime of psi. The first one is integrated over T, the other is integrated over R. And similarly, we have another equality like this. And clearly, this cannot be satisfied for mechanical systems for the reasons I explained earlier. But the question is, what systems can exist that satisfy these equations? And you see that psi is a quantity that needs to be integrable over both T and R. And similarly, psi prime should be integrable over R prime and T prime. Otherwise, these expressions make no sense. And this is possible, but only in the situation where the state of your system is not a mechanical particle that has a well-defined position, but the state of a system is some sort of a field. This is the only situation where this whole description makes any sense. It breaks, I agree, superluminal observers do not make any sense for mechanical systems, for classical mechanical systems, but they have a chance to make sense. Or, I mean, in principle, all these requirements can be satisfied for fields. So the conclusion, one conclusion you can take from there is that you should expect that if superluminal observers make any sense, that any reasonable physical theories must be field theories. Whether classical or quantum, I'm not going to talk about it today, but certainly not a mechanical system. And one last thing I would like to talk about is, well, two more things. An example. So Professor Birula asked us to present an example of Maxwell's equations. And in fact, you can develop the whole Maxwell theory in both subluminal and superluminal frames of reference. These are Maxwell's equations in all glory, written in the superluminal frame of reference. As expected, there are 3 times one space, but now the density of charges are 3-dimensional and current densities are 1-dimensional. So you can write these equations. They look different. They look the same in all superluminal frames, but they differ from Maxwell's equation in subluminal frames of reference. So that's the physical difference you get. And one last interesting, funny detail here if you consider a static case, you can retrieve the Gauss law, the familiar Gauss law here, but it's hidden somewhere else. So this is where you had Gauss law in subluminal frames. Now the Gauss law, if you take derivatives over time to 0, the Gauss law comes from these two terms. And this is the Gauss law written in the superluminal frame of reference. You have a derivative over space of electric field instead of divergence. And on the right-hand side, you have the vector of densities divided by epsilon 0. I found this quite charming, but to what degree this is important or not, I don't know. But what I do know is that you can write these equations. You can study the whole theory in superluminal frames of reference. Mathematically speaking, it makes sense. Also, mathematically speaking, it does make sense to talk about 3 times one space. You have to be careful about definition of velocity. You have to be careful about how you define dynamics. But other than that, in principle, special theory gets more weird, but it's self-consistent. I mean, at least we could not find any loopholes or inconsistencies. And we did spend some time on this before taking it public. So this you can be certain. Now, the one last important question I would like to address is whether this is just maths or it has any meaning in real world. Whether this has a potential to be tested, observed, whether superluminal particles exist or not. And for a long time, I thought that that's going to be the most difficult question because probably these particles do not exist. For reasons we do not understand, perhaps, but because we don't know why certain particles or fields exist and other don't. This is called standard model that comes out of the blue, but I have changed my mind over time. And I would like to show you an example where you could expect to see these objects. So if you go back a few years to the Nobel Prize awarded a couple of years ago for the discovery of a Higgs particle and Higgs mechanism, the usual story about Higgs mechanisms is that you have to, in quantum field theory, you have to have a quantum potential, whatever it is, defined in such a way that it has a degenerate ground state, or ground state is not does not follow the symmetry of the potential. Anyway, what you need to have is a field theory with a potential like this, where the ground states of the system can be here or here or here. The ground state expanded around the minimum will violate the symmetry of the potential, and that's the spontaneous force symmetry breaking, not only in Higgs mechanism, but also in other mechanisms. So the general, in principle, the ground state of this system is not here or here or here, but it's a superposition of that violates the symmetry. And but you can also expect that if you make an observation, if the field is observed, for example, due to some quantum fluctuation, can emerge in a state here or here or here. So the usual story is that you take this potential, then you expand your theory around the minimum, where the potential around the minimum is well behaved and is kind of has a well-defined minimum, and that's where you define your quantum field theory. And you say that effectively the ground state of your system is just here because the symmetry was spontaneously broken. And you approximately expand the theory, the Lagrangian and Taylor series, take the lowest terms. So for sufficiently low energies, what you observe is quantum field theory sitting here. And that's the conventional theory where you have massive Higgs particles and other particles, also other fields get mass due to interactions and so on and so forth. Now, the interesting part is that if you take a standard textbook on quantum field theory and open it on the chapter about this, the whole discussion starts with the following statement. You have equation for your Lagrangian for a scalar theory. And if you want that funny potential, that is this inverse Mexican hat potential, you have to start with the assumption that m squared is negative. That's what they say. Now, suppose that m squared is negative. In fact, this is the only mention of this. And in the whole remainder of the book, they don't even go back to this question, what does it mean, how to interpret this. And it's the same in all other textbooks I have found. You have to take a negative square mass or imaginary mass, if you like. And then you do your physics, do your math, do your magic, and eventually expand your theory in approximation somewhere around the local minimum. But technically speaking, a scalar field with a negative square mass is a tachyonic field. In fact, in quantum field theory, this is how you define tachyons, by saying that you have a, if that's non-interacting theory, Klein-Gordon equation with negative square mass. So technically speaking, the Higgs field before the breaking of symmetry is a tachyonic field, self-interacting tachyonic field that also interacts with other fields. And effectively, you can approximate that theory with a theory of massive subluminal particles. But for sufficiently large energies, you should be able to see that your field is not sitting in a minimum, but the whole potential is in fact shaped in the shape of a hat. So in principle, for sufficiently high energies, the guess or speculation is that you should expect that Higgs particles or these kind of effective particles that emerge in the theory should follow equation that involves negative square mass, which is the tachyonic field theory.
I would protest here because I'm not an expert in quantum field theory, but the one thing I know is that the mass, physical mass of a particle is defined by the second derivative of a potential at the minimum. So the fact that the parameter is positive and negative doesn't have any single physical meaning. That's why Średnicki never actually mentioned it anymore. This is just a parameter. And
yeah, that's what they
it
say.
doesn't have anything to do with what the physical mass of the particle is, because the physical mass of the Higgs, we know it's positive and it's something like 120 GeV. So we know that. And if you want to interpret this some negative object, some negative mass as a mass, you will need to change the definition of mass, and then also to extend it to the interacting quantum field theory in a consistent way. And I don't think it's gonna be easy, although I'm not claiming that it's impossible.
Yes, you are absolutely right about this. That's what they usually say in this textbook. You shouldn't bother about this negative mass squared, is just a parameter. Let's not bother about this. So what we have done so far, we have developed classical theory of tachyons, right? Now, how do you define a tachyon in quantum field theory? I could say that by definition, a quantum tachyonic field is one that has negative square mass. Now, whether this corresponds to superluminal propagation or not, and what are properties of these fields, this is to be studied. And in fact, people have studied this, and they have studied quantum field theory of negative square mass with even self-interactions. And Sudarshan was one of the first people to do that. And the funny thing here is that there is no unique way of doing that, because what defines quantum field theory is not just the equation, but also commutational relations of the field operator. And these are far from being straightforward. There are many ways of defining commutational relations of the field operator, and only some of these possibilities were investigated, and that happened before the discovery of the Higgs mechanism. So again, I agree that it is not straightforward to say what it means for the mass to be negative, but we can just define this to be a quantum field theory of tachyons and study that theory and see perhaps some link between that theory and the classical description I have given. There are some speculations that even if you have negative square mass, the propagation could be subluminal. There are also other authors that claim otherwise. So there is a discrepancy here. There is also no agreement whether these particles can be tachyons, it can be fermions or bosons. But again, I don't think that that this problem has been exhausted. In fact, it has been touched in the 60s, and then people have stopped being interested in that because there was no experimental evidence for these particles. Yet, if I was to point out any ray of hope to looking for these particles, I would say that that would involve the Higgs particle in the phase before breaking the symmetry. For sufficiently large energies, you should expect to see these effects, and then perhaps something interesting emerges that is other than the conventional quantum field theory. That's all I have to say about this, because this is obviously something that we have not investigated yet. That's the next step we want to look into. I don't know where does it lead to, all I can say. But again, it's not 100% excluded that this has anything to do with reality. So perhaps that classical theory I described does characterize something existing, some type of field that exists. In what form, it's yet to be determined. So with that, I would like to thank you for listening.
questions?
There is chat here also on Zoom, so. I hope it was sorted out. Did I turn the microphone on, by the way? Yes, okay, good. That would be more appropriate then. Yes.
Okay, so if I can ask, so if you treat these superluminal observers seriously, then you have to rule out the possibility of existence of like classical particles.
Yes.
So everything must be field. But then you still, your observers are still classical. So shouldn't you, to make it like fully consistent, shouldn't you go to like quantum observer description?
Yes, you are completely right. What we have shown that in a way this whole description is self-inconsistent. Because on one hand, we have an observer that moves along a given velocity v. On the other hand, the only physical objects that can be characterized are fields, right? So it's not the same. How do you construct an observer then? This is a problem, and this is not a problem only of this approach, but it is a general problem in quantum theory in general, right? You write Schrödinger equation in a given frame of reference, but what is a frame of reference that has x and t where any particle is smeared in space and there is no well-defined position for anything. So this is an open question, and at some point it will have to be resolved. There is something that is called relational formulation of quantum mechanics, and Carlo Rovelli was one of the proponents of this, where he tries to characterize systems not in terms of classical frames of reference, but in terms of relation to other quantum systems. So he's only looking at relation between different quantum systems, and then the whole picture makes sense. But in a way, you are correct. This is indeed showing that the whole thing is not self-consistent. But again, this is a problem of physics in general, not just this.
Yeah, of course. But maybe also because you have this thing that superluminal and subluminal are in a sense distinguishable, but maybe this will disappear if you consider proper observers. So observers that are fields, not, I don't know, it's just.
I would expect that there are physical differences, and there is nothing wrong with that. I mean, after all, in general, or even special relativity, you can consider observers that are different from inertial observers. For example, you can consider a uniformly accelerated observer, that I always like to do in my lectures. And this is an observer that has a different metric, is physically distinguishable from inertial observers, and yet he has different laws of physics, and yet everything makes sense because that perspective is also a valid perspective. You can look at reality from a non-inertial frame of reference, and you are allowed to do that. Your laws of physics will change, but so what? In fact, it's the same thing with these superluminal observers. The only subtlety here is that you have infinitely many of them, and they are all identical. So that's why you can call these inertial, just like you call all superluminal observers inertial. They don't share the laws of physics, and I don't have a reason to believe that they will share the laws of physics if you go to this generalized picture that you mentioned. I don't know how to do it, but I wouldn't be surprised if that is preserved in that case as well.
Can I ask a question about the sign of sigma prime and sigma that in the large V is what's that?
You mean this, yes?
Yes, it's a capital V is what is capital V in the last line?
This is a velocity. So if you are in a given frame of reference and you see a particle moving with velocity small v, then it has energy E, momentum P, given by these formulas. And if you want to transform to another inertial frame of reference, that is subluminal. So if you move with additional velocity V, then sigma will change from this to this.
In that reference frame, we will see different velocity, different actually superluminal velocity, right?
Yes, the velocity will also change, but on top of that, what will change is also sigma. So if you change the frame of reference, you have two alternative ways of making the transformation. Either you just treat it as a 4-vector and transform it according to Lorentz transformation, or you can not do that, but instead you can change velocity v into v prime and sigma into sigma prime, and the result is the same. And the result is such that energy can change the sign from plus to minus and vice versa.
So, any other questions? If not, let us thank you again.